Okay, this is the second video in my short little series on SHM Formulae and application. So it concerns exactly the same situation where we have a mass spring system. The mass is hung off a spring, it's displaced upwards by 0.1 meters and released, and it oscillates freely between a displacement of plus 0.1 and minus 0.1 meters. The time it takes for one oscillation is 2 seconds, and the frequency is therefore 0.5 hertz. The amplitude is 0.1 meters. Now, the formula I'm talking about this time is this one: A equals minus 2 pi f squared x, which we have also derived, and I've linked to a video of the derivation, so I don't want to derive that again. Now, A here is the acceleration of the mass. F is the frequency, which we know, 0.5 hertz. X is the displacement. Let's just take a minute to look at this and appreciate what it's saying. Okay, it's saying that the acceleration is proportional to the displacement. Okay, because this whole thing here is a constant. The frequency is constant, pi is a constant, 2 is a constant, that whole thing's a constant. Okay, so it's saying acceleration is proportional to displacement, but this minus sign says that it's in the opposite direction, which is the defining feature of simple harmonic motion. Okay, so what this is saying is the further you are, x, away from the equilibrium position, the greater A is the acceleration back towards the equilibrium position. And if you think that the acceleration arises due to a resultant force, and you're thinking F equals ma, then for this mass spring system that totally makes sense. Okay, if you drag the mass down, sorry, this mass is multicolored for some reason, if we drag the mass down, then the resultant force on it is greater and greater upwards, because the spring is pulling harder and harder, because the greater you extend the spring, the greater the force. So the greater the displacement away from equilibrium, the greater the force trying to restore it to equilibrium, F, therefore the greater the acceleration. Okay, so this sort of makes sense. So we derived this previously, we don't need to derive it again. Let's just get a feel for what it's saying. Okay, so let's just think, well, what is the acceleration at x equals, let's say, 0.1 meters? That is when it's at the very top. We're taking upwards as being positive. What is the acceleration? Well, we just plug the numbers in. A equals minus 2 pi times the frequency, 0.5 squared, times the displacement, 0.1, which is what? Let's give it a try. 2 pi times a half is just pi, so I'm just looking at pi squared, minus pi squared times 0.1, which equals minus 0.99 meters per second squared, rounded to 2 decimal places arbitrarily. Now, this acceleration is minus, which means it's negative, which means it's downwards. So the acceleration, when this is raised up by 0.1 meters, the acceleration is downwards, the resultant force is downwards. Well, that makes perfect sense. That is the case. Okay, what about when x is 0 meters, i.e. the equilibrium position? What's the acceleration going to be? Well, this one's going to be pretty straightforward, because we're going to have minus 2 pi times 0.5 all squared times 0, which is none other than 0 meters per second squared, i.e. no acceleration when it's passing through the equilibrium position. Okay, so this thing's going to be released from here. It's going to go, whoops, oh dear, it's all come apart. Here we go. It's going to go, come on, something like this. oscillate up and down, but when it's moving through the equilibrium position, it's not actually accelerating. Well, that makes perfect sense because it's called the equilibrium position for a reason. That's the position where it's in equilibrium and the resultant force on it is zero. Therefore, there is no acceleration. Very rapidly, let's try at a displacement of minus 0.1 meters, i.e. at the bottom, maximum bottom displacement. Okay, what have we got here? Well, A equals minus 2 pi times 0.5 all squared times minus 0.1, which equals, you'll see that this is just the negative of our very first one. Okay, 0.99 meters per second squared. So this is exactly the same acceleration as our first example when it was at the very top, except the acceleration is now positive because the resultant force is now upwards, so it's now accelerating upwards. Okay, so this is just plugging in numbers and getting expected values. Obviously, it doesn't have to be at some nice part of the motion. It could be at something like, you know, x is 0.08 meters. What's the acceleration? Well, plug it in, okay, and you'll find the answer. It's as simple as that. This formula is not particularly hard to get to grips with. Okay, so that's that. Now there's a couple of other things just to say, okay, about maxima and minima, because there are certain formulae for maximum and minimum this and that that you need to get a handle of, and they're actually pretty straightforward. So let's take our first equation from the previous video regarding the displacement of the mass over time. Okay, now this whole cos bit here can only ever vary between +1 and -1. Okay, cos of anything only varies between +1 and -1. Now if you multiply that by a, that means x varies between -a and +a. Okay, so the maximum x is +a, or just a. So the maximum value for displacement is a, the amplitude. Well, that's pretty straightforward. Okay, now let's take another expression which was on the other side. A equals minus 2 pi f squared x. Right. Now if we already know that x, our displacement, varies between -a and +a, and the maximum is +a, or a, then we could just substitute that in here if we want to find the maximum for a, because all this stuff here is just a constant. So therefore a varies between minus 2 pi f squared times -a and minus 2 pi f squared times +a, which is just 2 pi f squared a and 2 pi f squared minus a. So maximum a is, we'll take the positive one of those, 2 pi f all squared a. So if you're asked to find the maximum displacement, that is just the amplitude. If you're asked to find the maximum acceleration, it's 2 pi f squared, 2 pi f all squared times the amplitude. Now there's one other maximum that you need to know about, and that's the maximum velocity. Marginally tricky, but not the end of the world if you're happy with I mean, the derivation of it is marginally tricky, but the answer isn't. Okay, it's somewhere between the displacement and the acceleration. So x is a cos 2 pi f t. We know that. That's our top formula. Okay. Now look, this is A-level math, so if you don't do it, don't worry. But v is dx by dt, which is, if we differentiate cos, we're going to get minus sine, and we're also going to get all this stuff here if we're differentiating this whole expression coming out the front. So we're going to have minus 2 pi f a cos 2 pi f t. Okay, that's our expression for v velocity. Now look, all of this stuff, as before, varies between -1 and +1, all of the cos stuff. Okay, so our velocity is just going to vary between minus 2 pi f a and plus 2 pi f a. Okay, so therefore our final expression is maximum velocity is 2 pi f a. Okay, so that's 3 expressions. Let's just put them all together so we can see them all. The maximum displacement is just a. Okay, the amplitude defined. Maximum velocity is 2 pi f a. Maximum acceleration is 2 pi f. Sorry about that. Let's write that out bigger. 2 pi f all squared a. Okay, none of these are tricky to plug the numbers into. Okay, you just got to keep an eye on units with those, and you should be fine. So that is most of the formula on the formula sheet talked about. There are a couple more which we're going to deal with next week that aren't functions of time, okay, as this one is. So this formula here is all about how things vary with time. It's about the other one is a function which is about distance, how certain things vary with the displacement, sorry, from the equilibrium position. But we'll deal with that next week. So I hope this might have just cleared these things up a little bit. What you really need to do now is just practice applying these by doing lots of questions.